Nuruzanani binti Jamal from RAS 2034A. I will start explain with Kepler's first law known as law of ellipses. What is law of ellipses? Law of ellipses states all planets are orbiting in ellipse with the sun located at one of the foci. Before we go far with the law of ellipses, what is ellipse? So we need to make some recall about ellipse. This is shape of ellipse. As we know, ellipse has three properties which are have two focus, eccentricity and major axis and minor axis. Next is the properties of ellipse. First property is ellipse has two focus. When the focus together called foci, the sum of distant foci from any point on ellipse is always constant. Second property is eccentricity. Eccentricity is amount of flattening of ellipse. When ellipse flatter, the eccentric are more. Third property is major axis and minor axis. The longer axis is major axis, while the shorter axis is called minor axis, and the half of major axis is called semi-major axis. As we can see, a planet orbiting the sun in a shape of ellipse. The center of the sun always located at the one focus of the orbital ellipse, and the sun is at one focus. The planet follows the ellipse in its orbit, meaning that the distance planet to sun consistently changing as the planet goes around its orbit. This formula is to prove Kepler's first law. The main formula used is a general differential equation for the orbit of a particle in any center, isotrophic field of force, and then the orbital equation for the specific case of an inverse square law of force. We can conclude the orbits of the planets are not circles, but were instead the elongated or flattened circle that geometers call ellipses. We must remember sum of distance between each point of focus and any point on ellipse is constant.
Hi, my name is Nurul Najwa binti Abdul Aziz from RAS 2034A. I will continue explain this subtopic for law of equal areas, which is the second law in Kepler's planetary motion. So here we go. So, what is actually law of equal areas in Kepler's planetary motion? First thing is we need to understand the meaning of this law. I put here three laws with the meaning, but now we only need to focus for second law. The meaning of second law of Kepler's planetary motion is planets covers the same area of space in the same amount of time no matter where it is in its orbit. Let's look at for more details about this law. First, this empirical law discovered by Kepler arises from conservation of angular momentum. Second, planet performs an elliptical motion with a constantly changing angular speed as it moves around its orbit. Third, an imaginary line joining a planet and the sun sweeps out an equal area of space in equal amounts of time. So, from this figure we can see there is perihelion and aphelion. The point at which the planet is close to the sun is known as perihelion, and the point at which the planet is farther from the sun is known as aphelion. When near to the perihelion, more kinetic energy, while when near aphelion, less kinetic energy. Also, more speed at perihelion and less speed at aphelion. The planet will move faster when it is closer to the sun. It moves through a larger arc in a given time. The larger arc is just offset by the shorter distance, while the planet moves slower when it is farther to the sun. It moves through a smaller arc in a given time. The smaller arc is just offset by the longer distance. So, let's look at the example here to make it more clear. Basically, from this figure, we can see that each area is equal, but the arcs that sweep out the areas are not. The two effects exactly counteract to give equal areas. So, we can conclude that in order areas to be equal, the planet must speed up as it gets closer to the Sun and slow down as it moves away. So now we go next to the formula of law equal areas. This formula shows the Kepler's second law is actually consequence of the conservation of angular momentum, which holds for any system with only radial forces.
Assalamualaikum warahmatullahi wabarakatuh. My name is Noraina Hanum binti Abdurrahim, and I will tell you about the Kepler's third law, which is the law of harmony. In the previous slide, you have learned about the first and the second law of Kepler's. So, what is the third law? The third law name is the law of harmony. Kepler's third law has been published in 1619 in the book named Harmony of Worlds. Kepler noticed something curious. The time it takes for a planet to orbit the Sun, its orbital period P, is related to its average distance from the Sun, its semi-major axis, in a very specific way. So, let's dig into the conceptual definition. A planet farther from the Sun has longer path than a closer planet, but it also travels slower since the Sun's gravitational pull on it is weaker. Therefore, the larger a planet's orbit, the longer the planet takes to complete it. Besides having conceptual definition, law of harmony also have mathematical definitions. The square of the period t of a planet orbit is proportional to the cube of mean radius r of its orbit. For your information, t is period, and in this third law, period is how long a planet to complete one orbit around the Sun. For Earth, it takes around 365 days. Did you know that the mean radius is average distance between a planet and the Sun, and average distance between Earth and Sun is about 150 million kilometers? So we already well informed about the mathematical and conceptual definition of Kepler's third law. Let's know the fact of Kepler's third law. First, the ratio of the square of the revolutionary time periods to the cube of the average distance from the Sun is the same for every planet. This is because Kepler's third law says that the two quantities are proportional. In other words, if you take t squared and divided by r cubed, the answer will not change. It is constant in the orbit of any planet. Second, satellites orbiting the Earth also have the same ratio of satellites period squared to the average distance from Earth's cube. Last but not least, planets with smaller orbit move rapidly and have smaller period. Kepler's first and second law has their own formula. So did you think Kepler's third law has their own formula? The answer is yes. Kepler's third law, which is law of harmony, also has their own formula. Harmonic law can be derived from the Kepler's second law, which is A dot equal to L over 2m. We can change the L into the period and angular momentum per unit mass. So, the equation will become A dot equal to ml over 2m. And we can cancel out the m. So the equation will become A dot equal to L over 2 and A dot is equal to dA over dt. So we can integrate and the equation will become T equal to 2A over L, which is the period. You must remember that A is area of an ellipse. So A equal to pi AB, and we can substitute it into the A in the previous equation. B also can be substituted into the square root of 1 minus epsilon square A. So when we replace it into the equation will become T equal to 2 pi A square root 1 minus epsilon square A over L. And we can square both sides and do the mathematical operation. The equation will become T square equal to 4 pi square A cube alpha over L square. And we can derive it again, and the equation will become T square equal to 4 pi square over GM A cube. Besides derive it from the Kepler's second law, we also can make the derivation from the F central equal to F gravity. F sub C is equal to mv square over r, and F gravity is equal to G capital M and small letter m over r square. So we have to do the mathematical operation, and we will get V square equal to Gm over r. So remember that V equal to 2 pi r over T, and replace it in the V position, and don't forget the square. Once again, square both sides and do the mathematical operation, we will get t squared equal to 4 pi squared over gm r cubed. So this is the formula of Kepler's third law. We can conclude that Kepler's third law is somewhat different from the other two. It is more mathematical than the first and second laws, allowing a calculation to be made of the period of the orbit if the radius is known, or the radius to be calculated if the period is known. More precisely, it states that the square of the period of the orbit is proportional to the cube of the radius. This applies not only to planets orbiting the Sun, but also to satellites orbiting the Earth, and is therefore important in space technology.